Calculating limits using limit laws. So in the previous section, we saw some of the pitfalls of estimating limits using graphs and tables. One of these was in that problem with the oscillating function. Let's go back to that really quickly. Okay, in example 3, when we looked at the table of the sine of pi over x as x got closer and closer to 0, we got the false conclusion that the limit is 0, because for all of these different x values, both negative and positive, both from the left and from the right of 0, we found outputs or y values all equal to 0. But this was in fact not true. So looking at the graph showed that this was an oscillating function with a limit that does not exist. So using a table alone can potentially lead us to a false conclusion, and sometimes our graphs can be a little bit difficult to look at. So we've got a new method for today, and it's going to make our lives a whole lot easier. And so this lesson is all about calculating limits algebraically. Now we have a method for algebraically finding the limits of infinite functions, but we don't know what to do algebraically about any other type of function at this point. So if f is a polynomial or a rational function, and a is in the domain of f, then the limit as x approaches a of f of x is equal to f of a. This is called the direct substitution property. All this means is that what we're going to do now is we are going to plug a into our function. This is kind of what we did in infinite limits. So direct substitution means we are going to start by plugging in x equals a. We're going to plug this into our function. We have a few other properties of limits, and these might seem a little bit obvious, and they kind of are. So we've got the sum law that tells us that the limit of two functions, f of x and g of x, the sum of these limits as x approaches a is equal to the limit as x approaches a of f of x plus the limit as x approaches a of g of x. We've got the same idea for the difference law, that the limit of a difference is just that limit of the first function minus the limit of the second function. Kind of a little bit obvious. The constant multiple law basically tells us that if we have a constant times a function, well, we can pull that constant out to the front of our limit. We've got the product law that tells us that the limit of a product of two functions is the product of those limits. We've got the quotient law. Quotient means dividing, means you divide these values and you get a quotient, that f of x divided by g of x, the limit of this expression is equal to the quotient of those individual limits. We have an important qualification here. The limit as x approaches a of g of x must not be equal to 0, because we know that a denominator cannot be equal to 0. We've got the power law that tells us that the limit as x approaches a of a function to some power is the limit of that function raised to a power. And the same thing with the root. We've got a similar root law that tells us that the nth root of a function, that limit is equal to the nth root of the limit of that function. And this is true where n is a positive integer. And we make the note that if n is even, we assume the limit is greater than 0. Because if we're taking an even root, we know that this must be positive. If we have a negative inside of an even root, then that gives us an imaginary number, which we're not going to worry about in terms of limits. And finally, the limit of a constant just states that the limit as x approaches a of any constant is just that constant. So I want to talk about this last one really quickly. What this means is that, let's say I have a function f of x is equal to 5. Let me graph this function. Well, f of x is equal to 5 is also y is equal to 5, so that's going to be a horizontal line. F of x is equal to 5. Now let's say I want to find the limit as x approaches 3 of 5. so of this function. Well, what I'm saying is that what does the y value approach as x approaches 3 from the left and from the right? Well, as x approaches 3 from the left and from the right, can I see that y still approaches 5? And so my limit as x approaches 3 of 5 will be 5. So that's what this constant, this limit of a constant means, that the limit of any constant is just that constant for this reason. All right, so now let's use the limit laws and the graphs of f and g to evaluate the following limits if they exist. So starting off, we've got the limit as x approaches -2 of f of x plus 5 times g of x. Now what my sum law tells me, that I can split these limits up so that this is the same thing as the limit as x approaches -2 of f of x plus the limit as x approaches -2 of 5 times g of x. My sum law tells me that I can do this. The next thing I want to look at is the limit as x approaches -2 of 5 times g of x. Well, I've got this other law, the constant multiple law, that essentially tells me that I can pull this constant out of the limit. And so I can say that this is equal to the limit as x approaches -2 of f of x, plus I can pull this 5 out to the front, plus 5 times the limit as x approaches -2 of g of x. So now that I've got this broken up a little bit better, and let me give myself a little bit more room here. And so now I'm just finding the limit as x approaches -2 of f of x and the limit as x approaches -2 of g of x. Okay, let's do that. F of x, so f is this pink curve or this red curve, this top curve. And so what happens as x approaches -2? As x approaches -2, well, -2 is right about here. This is 1, this is -2. Well, I'm looking at the left and the right. So what happens as I'm approaching -2 from the left and from the right? And I'm looking at this top curve. Well, following this curve from the left, it looks like I'm approaching +1. Following this curve from the right, it looks like, again, I'm approaching +1. And again, it doesn't matter that the actual value of f of -2 looks to be more like 2. I'm just worried about what happens as we're approaching -2. And so this limit is +1. And so the limit as x approaches -2 of f of x is +1. Now I'm adding to it 5 times the limit as x approaches -2 of g of x. So now I'm looking at this bottom curve, this blue curve. And I'm seeing what happens as I get closer and closer to -2 from the left and from the right, following this blue curve. Well, now it looks like from the left and from the right, I'm getting closer and closer to what looks like -1. This looks like -1. And so this limit is going to be a -1. And because of my constant multiple law and my sum law, I can just perform this algebra. I can just say 1 plus 5 times -1. Well, that's the same as 1 minus 5. And so this limit is -4. This limit is -4. All right. So next I'm looking at the limit as x approaches 1. And now I've got a product, f of x times g of x. And my product law tells me that I can split these up. And so I can say that this is equal to the limit as x approaches 1 of f of x times the limit as x approaches 1 of g of x. And so now let me just look at my graph. And let's see what's happening at 1. So we have x of +1 right here. And let's start by looking at the limit of f of x. So I have my top f curve, and I'm seeing what happens just to the left of +1 and to the right of positive 1. And if I trace this curve, I can see that from both sides, as x is getting closer to 1, y is getting closer to what looks like 2. And so my limit as x approaches 1 of f of x is 2. My product rule tells me that I'm multiplying this by the limit of g of x as x approaches 1. So what's happening to g of x as x approaches 1? Well, if I look slightly to the left of 1, I'm following this curve down here. And so this looks like a limit of, let's mark this on our graph, this looks like a -2. It looks like I'm getting closer to y equals -2. From the right, if I look slightly to the right of 1, I'm following this other curve right here. As I'm getting closer and closer to x equals 1 from the right, y is getting closer and closer to -1. So let's do a little side note. My limit as x approaches 1 from the left is -2, and then the limit as x approaches 1 from the right is equal to -1. And for that reason, the limit as x approaches 1 of g of x does not exist, because the left and the right-hand limits are not the same. The limit as x approaches 1 in general of g of x does not exist. And so if we have a product and one of the limits is equal to 2 and the other one does not exist, then our conclusion is that the limit does not exist in general. If one of these limits doesn't exist and we're taking the product of a limit that exists and then something that doesn't exist, then our limit just does not exist. Okay, now we've got the quotient rule. So we are taking the limit as x approaches 2 of f of x divided by g of x. And we know, thanks to our rules, that we can split this up. We can split this up into the limit as x approaches 2 of f of x. And we can divide by that limit as x approaches 2 of g of x. And so as x approaches 2, so now I'm looking at where x is equal to 2, which is right here. I'm looking at the curve f of x, and I see that as x approaches 2 from the left, I'm getting closer and closer to this value. Now, I'm going to have to estimate this value. From the right, as g of x gets closer and closer to 2, again, I'm getting close to this value right here. And I'm just going to have to approximate this. So it looks like it's a little bit, it's between 1 and 2, and it looks like it's a little bit below halfway between 1 and 2, so I'm going to call this a limit of 1.4. I'm going to say this is about 1.4. And then my limit of g of x as x approaches 2, well, from the left and from the right, we're approaching y equals 0. It looks like this curve just passes through the x-axis at 2. So in this denominator is going to be 0. But remember that we can't actually have this because the quotient rule is only true if the denominator is not equal to 0. So what are we going to do about this? Well, since we can't actually use this quotient rule and our numerator is approaching a non-zero number and our denominator is approaching 0, then again we are going to conclude that the limit does not exist. So this limit does not exist. All right, so now let's explore some situations in which we're actually given the functions rather than a graph. So in example 2, we want to evaluate the following limits, and we're evaluating all of these limits algebraically. And using all of these rules, what this essentially tells us is that, well, first of all, we have the constant rule. the rule for the limit of a constant. And we said that as x is approaching any value of a constant, the limit is just going to be equal to that constant. Next, we can just use the direct substitution rule. And in all of these other problems, we can use the direct substitution law. And when we mix the direct substitution law with all of these other limit laws, what this essentially means is that we are just plugging in x equals a into this function. If we get something that doesn't have a denominator of 0, then that's the limit. And so if I plug in -4 to my function x, I get that the limit as x approaches -4 of x is just -4. How easy is that? In part C, I'm finding the limit as x approaches 2 of x squared. Well, I'm plugging in my value of a, so this is going to be 2 squared, which is 4. Part D, the limit as x approaches -3 of x squared plus 4, I'm just plugging in -3. And so this is going to look like the quantity -3 squared plus 4, which is, well, when I square a negative number, it becomes positive. So this becomes a positive 9 plus 4, which is 13. And finally, when I plug in 1 to x squared plus x plus 2 over x plus 1, I'm going to get 1 squared plus 1 plus 2 divided by 1 plus 1. In my numerator, I have 1 plus 1 plus 2, which is 4. In my denominator, I have 2. I always want to simplify this fraction as much as possible, and I know that 4/2 is just 2, and so my limit is 2. If I look at this graphically, let me graph part D. I'm going to graph x squared plus 4. Use a standard window. I know that this looks like a parabola that's shifted up 4 units, x squared plus 4. And so what I'm saying is that what happens as x approaches -3, well, my y value is going to approach 13. Because this is a continuous function, the limit is just equal to the function evaluated at this point. And so by the direct substitution law, the first thing we're always going to try is we're just going to try to plug this value of a into our function. And so this is our introduction of some of those limit laws.